Hi, everybody. Thanks for having me. My name is Irfan Ahmed. I'm going to be talking about interrupts, kind of an unusual topic hidden deep down inside. There's a bunch of you with your laptops open, a bunch of you with Macintosh laptops. So when you get bored of me, just type in this command called latency. And so you'll say it's like pseudo latency you'll have to do, and you'll see what your interrupts are doing, or what type of interrupts your systems are receiving when you get bored of me. So a little bit about me. Systems guy, pretty much from start to end. I've written a few operating systems in my life. Founded this company called Cloud Physics 5 years ago. Before that, I was at VMware, worked on the virtual machine monitor. A bunch of my colleagues are here from that time, as well as distributed systems. Before that, I was at Transmeta, where I helped develop their x86 compatible software-based microprocessor. So I got into interrupts a few years ago. Obviously, had to deal with them as an operating system engineer. But then after years and years of working on them, and especially around performance optimization, I came to a point where, for every 6 months of work that I would do, I would end up with a 0.25% barely measurable performance improvement. And one day I just sat back and said, this is not a good way to live life. So I'm going to try to do some actual, real computer science here and try to see if we can make bigger improvements. And this is the story of my journey. And journey started, of course, of interrupt starts back in the 50s. I'll talk about that and the journey forward, and I'll tell you where my journey with this began and the interesting stuff that I found from the history of interrupts and where we ended up taking it. Okay, so here's the outline of the talk. Interrupts, lots of interrupts. I probably want to fix that. Oh, there we go. Okay, not sure what that was. Okay, so so this is just a quick timeline for those who skipped that class in university, in undergrad. So we have a bunch of timelines here. We've got a timeline for the user application, of course, the kernel and the interrupt handler. So this is all software. Now, interesting thing about computers we often don't realize is that there's actually multiple computers inside your computer. So the I/O device is a totally separate computer. It's got its own control flow, everything totally independent. And it's got some wires that reach into the processor to do what? Interrupt. Okay, so that's this job in life, is, hey, I want to interrupt. Right? It's like my kids. Right? Last night when I was preparing this presentation, I got all kinds of taps on my shoulder. So it's just like that. So there are little computers running around, these things called I/O devices. So let's say there's a user application running, and all of a sudden an interrupt comes because of some I/O completion. So that interrupt gets fired, and of course the user application running on that process gets interrupted. And so now the interrupt handler is running. Typically there'll be some amount of work in the interrupt handler, some amount of work in the kernel to actually figure out what to do, vector it, and so forth. And then the user application will start again. Okay, so later on, the user app, let's say, wants to do some I/O of its own, right? So maybe it will do that, and you'll end up in the kernel. The I/O will get requested, and then the application will continue. And then this cycle just continues all the time. So right before this talk, a couple hours ago, I started pseudo latency on my laptop. And in between then and lunch, I ended up with 2 million interrupts that I counted. Right? So that's how much interrupt activity is going on your laptop. We just don't think about it. Okay, so let's start this journey of interrupts here. So how many of you have heard of this guy called Dijkstra? Okay, maybe about 60%. That's okay. That's okay. We'll introduce you to Dijkstra pretty thoroughly in this presentation. So I'll let you read this, okay? Here's what he said about interrupts in his manuscript 1303. He's famous for writing hundreds of manuscripts and not really publishing them. I mean, just, anyway, strange guy. So this is Dijkstra talking about, and by the way, the capitalization is not mine. That's actually from his transcripts, right? So he calls interrupts a box of Pandora. So Dijkstra's work on interrupts starts in 1957. And the machine that he worked on at that time was this fascinating machine called Electrologica X1. So let's do a quick poll. 57, right? Let's do a quick poll. Raise your hand if this is the first time you're hearing about the X1. Come on, everybody. There's 2 people there that have heard of it. That's awesome. That's awesome. Okay. Okay. So this picture, for those of you who may have raised their hands, might jog your memory. So very interesting machine from a historical perspective, but I digress. Okay, so let's come back to interrupts. So this is a machine that that Dijkstra is working on for interrupts. And here's what he had to say about it. I'm actually going to read this out. Okay. And so he says, halfway through the functional design of the X1, I guess early 1957, Bram Dijkstra and Carol Schulten confronted me with the idea of the interrupt. And I remember that I panicked. Being used to machines with reproducible behavior, how was I going to identify a bug if I had introduced one? He says, after I had delayed the decision to include the interrupt in the X1 for 3 months, Bram and Carol flattered me out of my resistance. It was decided that an interrupt would be included, and I began to study the problem. I mean, the whole passage is fascinating. But first of all, who is this dude, right? Edsger who? Okay. So he's a Turing Award recipient, rare Renaissance man in computer science, programmer and theoretician right at the founding of our discipline. Before this, computer science was even known as computer science, right? You know him from your undergrad course in graph theory or other networking or systems as having done or designed what's called the Dijkstra's algorithm. Now it's been improved since then, but even the A-star algorithm is basically based on this. He coined the term structured programming for the first time. One of his operating systems was the first time, if you look in history, that is layered. So he was doing software architecture before software architecture was a thing. He wrote the first paper widely recognized in concurrent programming. And he's famous for the consider harmful theme, or meme. And I've used it, and without even knowing this, it comes back from Dijkstra in the past. So let me prove this to you. This is 1968. Letters to the editor for the ACM, Communications of the ACM, which is a fabulous journal. If you don't subscribe to it, please do. It's absolutely fabulous. Okay, so I've highlighted. He says, the quality of programmers is a decreasing function of the density of go-to statements in the programs they produce. Later on, he says, I became convinced that the go-to statement should be abolished from all higher-level programming. And this, my friends, right here is where that movement starts. The structured programming movement starts right here, 1968. Okay, so now let's go back. Here's Dijkstra again. Now we know him a little bit better. So he's got chops, right? I mean, we're not talking about a soft person here, right? This is a hardcore Renaissance computer scientist. So when he says that he was confronted and panicked, this is serious stuff. Now we take it for granted, right? I know you're running pseudo latency right there. I'm sure you are. So it's easy, right? Just pseudo latency, and we can see a number of interrupts. But this is like at the dawn, right? There is no such thing. And some of his colleagues are confronting him, and of course he refuses to do it until he's flattered. So nothing's really changed, right? So if you want to take a hard problem and get somebody to work on it, just flatter them. Okay, it worked for Dijkstra, it can work for anybody. Okay, so he goes on to design the interrupt handler scheme for the X1. It's comprised, according to his manuscripts, of about 900 instructions to handle interrupts. And it formed a part of the work in his PhD. Okay, so now we know that computers didn't always have interrupts. Okay, so Knuth actually credits Dijkstra with the independent invention of an interrupt system, but historically, Dijkstra was not the first one. Okay, but those things happen kind of independently, like all cool things. People start to think about them around the same time. So this is Dijkstra's nemesis from those days, as I've shown you. He was scared of interrupts due to the difficulty of debugging, but he figured it out, and a few other teams figured this out as well, and I'll show you what those are. But there's a remaining problem, okay, that wasn't really addressed then up until perhaps the 70s. And that's the problem of what happens at high I/O rates. Now, this little computer, like your kid who taps on your shoulder all the time, well, if that happens a lot, like in modern systems, there's a lot of I/O, right? The rates are very high. That leads to a lot of interruptions, which means that very little work gets done, right? So my talk wasn't done until this morning. Okay, so what's the solution? It's called interrupt coalescing, but I digress again. So we need to go back to our story, and then we'll come back to coalescing in a bit. Okay, so in actual fact, in 1954, the NBS DCAC was the first machine to have an I/O interrupt. Now, there were machines before this time that had something like an interrupt. For example, the UNIVAC one had an overflow trap, okay, as you'd expect, right? I mean, some kind of counter. But not specifically an I/O interrupt. Okay, so the DCAC is the first machine, 1954. So this is an independent invention, right? So now the UNIVAC 1103 had this really interesting wind tunnel interrupt, right? This is like, if you think back to 55, really interesting use case in the early days using interrupts for real-time data collection, right? Now to get to the time of Dijkstra, when he was working on this problem, we have to fast forward to 1957. Okay, so I have two dates here. So 57 is when he's working on it. 59 is when his dissertation is published. Very private guy, he doesn't publish. He publishes, but doesn't circulate it very widely. In the meanwhile, other teams are working on the same problem. So, so we know of the IBM Stretch system, which I believe there is one at the Computer History Museum. Okay. And we also know about the Lincoln Labs TX2. Now, who's heard of the Lincoln Labs TX2? One of the most interesting, fascinating machines, in our history. And I'll talk a little bit about the TX2 in a second. So the TX2 and the IBM Stretch are examples in the US, and of course, at that time, Dijkstra was working in Europe, right? So the X1 had this really nice vectored interrupt system, which is kind of also present in some of these other systems that are shown here. Okay, the TX2. I can't wait. I got to just mention it now. Okay, so the TX2. So anybody heard of Ivan Sutherland? Absolutely. Okay, so Ivan Sutherland is famous for a bunch of things, obviously, but his 1960s demonstration of basically what is a pen tablet system, right, which wasn't repeated really and done again for decades afterwards, is famous. And if you haven't seen the video, do yourself a favor, just like write it down on a piece of paper to say, when I go home tonight, I'm going to look at Ivan Sutherland's Sketchpad demo. And so that's what the system was called. Well, it turns out the Sketchpad and the videos on YouTube that talk about the show of the Sketchpad are actually on the TX2. So now again, we're back in the late 50s for that system. And the TX2 is one of the first systems that had a vectored interrupt, right? So you see all these threads that start to come together. Okay, so by 1960 now, pretty much every machine being built has some sort of a vectored interrupt support. And those that don't, because not all did, those that don't are actually very deliberate design choices. So for example, for experimenting with what happens if you don't have interrupts, like what type of programming models do you have to deal with, right? Or what type of I/O systems. Or to try out alternatives so for example, some of the Cray machines were explicitly built to do polling and not interrupts, which is the alternate to interrupt-based systems. So in the 1960s, deferred interrupt handling starts to get used as well. Okay. So, and for those of you familiar with the Linux kernel, you'll see that deferred interrupt handling is still part of what we have in our modern operating systems, and Linux is obviously not the only one. Interestingly, this technique seems to be one that has been adopted and dropped a few times, right? This deferred interrupt handling. For some strange reason, I don't know, maybe we just forget cool things sometimes and have to reinvent them. Okay, so 1966, you have the Burroughs B5500. Fascinating machine. If you catch me in the break, I'll show you a brochure of how the B5500 was advertised. It's very cool. So B5500 adds an instruction to test for additional interrupts before returning from the handler. So this is around the time you start to have this thing of, what do I do? Like, look, the interrupts are starting to be frequent, so maybe I want to do some kind of collapsing of them so I don't have to handle all of them at the same time. So it's the first example that I could find. So by the early 1970s, 3 interrupt overhead optimization design patterns have already emerged. Okay, so interrupt coalescing, the first pattern I could find was around 1971. By the way, note to folks, if you're ever trying to do historical research, don't just look at papers. You've got to look at patents. Because a lot of work that gets done in our industry is never really published in terms of academic papers, but it is all in patents. And too often I find related work sections in academic work, for instance, not go back and look at patents, which I think is unfair, and we can do better than that. So I talked about 3 interrupt overhead optimization design patterns that are starting to emerge. So the first of them is on an interrupt, try to complete more than one I/O. Okay, so this is a cousin to the technique of the B5500, which is kind of like the dual of that technique. The second technique is spin weight a little bit before dismissing the handler. Interesting. Probably wouldn't work necessarily these days, but it was done as a software operating system technique. Okay. And then finally, the third technique, which is the hardware technique, is after dismissing the interrupt, get the hardware I/O controller to delay the next interrupt. Right, this is like my kid tapping on my shoulder, and I say, okay, fine, I'll help you in this one, but you got to give me 5 minutes before the next interruption, right? So this is used and still used today. So again, going back to the 1970s for techniques that are still in use today. So now we fast forward to the 90s, starting to see high-speed devices really take off, like Ethernet, SCSI, both of them still around in their nth incarnation. And the resulting research starts to yield very interesting designs and dozens of patents in the area of interrupts. Now, around this time, the history of the development of the interrupt actually becomes the history of interrupt coalescing. So that's what I started to talk about a couple of slides ago, right? So anytime you're going to do that with these really, really high-speed devices, you're going to have to deal with interesting challenges around the performance of these systems. And of course, the competition in this field got very intense with network interface cards and SCSI cards that we saw a lot of innovation. Okay, so it basically boils down to two different parameters. The first is, and these are my terms, they're not otherwise very hard to explain, so I just came up with a quick two terms here. MIDL, which is maximum interrupt delay latency, which is what I would tell my son. Hey, give me 5 minutes for the next interrupt. Even if you've got a lot of things piled up that you want to tell me about, you got to just give me 5 minutes. So that's that one. And then the maximum coalesce count is number of things that are piled up to tell me about. If they cross a certain threshold, just don't wait for the other timer, the MIDL timer to expire, okay? So those are the two, and then all of these techniques are all about how do we play with those and modify those, okay? So in 1998, we see the first breakthrough for storage devices, and this is an LSI logic interrupt coalescing patent, which uses not just MIDL and MCC, but also this really interesting trick that says, hey, we can track the number of commands that are outstanding to the device. It's called commands in flight. If we can track the number of commands in flight, then we can do even more interesting things. And we can, in their case, they were using it to set delay timers. Okay, so then we get to 2008, which is kind of where I entered this picture and how I learned about all this sort of stuff. And we tried to take it further and not just be stuck on the previous literature and try to do some new things. So I'll talk about that in a second. So as I was researching in this area, I found out a lot of things from Mark Smotherman, who is at Clemson. He's got a great website, which I referenced at the bottom. I'll make the slides available. Not just about interrupts, but the history or the early days in computers, which is a valuable source and great. I'll give credit to him for having collected it from various scientists over the years. So as I was researching this, if this was a few years ago that I went through the exercise and I counted 4 Turing Award recipients who, at some point in time or another, appear to have contributed to interrupt processing. So this is Dijkstra, who we know really well now, John McCarthy, Corby from MIT, and Butler Lamson. So it's been a very interesting experience learning about these guys. Okay, so high I/O rates, right? So coalescing seems obvious, right? So here's pictorially represented. I/Os are being received, but no interrupts are being fired. So that's what's happening on the timeline. And eventually, an interrupt is fired, right? Basic technique, coalescing, not that hard. It's just a fancy way. So in this case, we're doing 1 out of 6 I/Os. So that's the delivery ratio in this scheme, okay? But here's the problem. Suppose those first 5 I/Os are received, and there's a huge gap until the 6th. Then the application will receive high latency, right? So now what do? You add a timer. That's easy, usually, because you have a separate computer, and this embedded computer called the I/O device has its own very, very high resolution timers. So modern devices are able to do, for instance, less than 10 microsecond timers in that embedded device, right? Exceptionally, exceptionally fast. Okay. So this is all fine and dandy, and ends up in a kind of a interesting, fairly simple system, and it's been quite successful. And we've scaled to a single card doing 40 gig, 100 gig because of this technique. If we didn't have this technique, you wouldn't be able to get to 100 gig networks today. Okay, so I/O devices are embedded computers, and hardware I/O controllers have separate processors, and they can set these really, really high resolution timers. But on the right-hand side, I'm talking about what's going to happen when you try to do anything other than a completely separate computer that has to do this type of processing, right? So it turns out that that's really hard, because now you, and especially in, like, say, KVM or something, your I/O devices are emulated. Right, so you can't run a 10 microsecond timer. You do nothing but just service timers on your CPU. You just run out of CPU, right? You just can't do that. And so a bunch of techniques had to get invented to be able to handle that. And most of them have to do with firing virtual interrupts from timer handlers, but it just got out of control. So early history of virtualized systems, right? This was a huge, huge problem until a few different techniques were invented. So here's the set of techniques, the contrast, right? The challenge, the difficult trade-off here. So on the top, you've got lots of timers being issued. The nice thing is you're going to get low latency, because as soon as there's an I/O, you're going to be able to catch it because there's a timer that's going to fire right after. but you end up with high CPU usage. On the other hand, you could have high latency but low CPU usage, right? So there's really no easy way to do this in the middle. And the conclusion is that timers suck. Okay, they just do. Like, I mean, you know. Okay, so now the interesting question is, of course, to get to this question took about 40 years of pain. Can we limit delays without using timers at all? Right, so that's the key challenge. And so there's one neat trick that I'll talk about, and I'm motivated, and then I will end there, and hopefully you'll find some interesting stuff that you heard about today that will motivate you to go and read up more about it. So here's a neat trick. Suppose instead of using timers, you take the actual I/O completions that the I/O device is getting, right? And you use those as timers. Okay, well, that's interesting, because the network card is just going to beep whenever it's going to beep, right? So we could use it, but there's some problems. It's kind of funky, because you can't just, normally we like our timers to be programmable, right? You can't program this. You can't predict when the network is going to interrupt you. So it's a little funky, okay? But what if instead we just piggyback our logic on top of this and just deal with the fuzziness of the uncertainty of when this particular fake timer is going to fire, right? Okay, so that starts to motivate our thinking to say, well, we're just going to kind of generally adapt ourselves dynamically around this unpredictable I/O rate. So even though we can't predict it, but we can kind of measure the last few, and we're going to say, oh, okay, unless things change dramatically, I'm kind of getting interrupted this often down in the hardware. So now I'm going to just assume that for the next time interval, it'll be similar, and that's going to be my timer, right? So now we don't need CPU timers anymore. We can just piggyback off of this. So that's a key innovation and got a huge performance improvements. The second innovation, as I get ready to close here, is this interesting concept of commands in flight, which I mentioned from the LSI Logic 1998 patent. So here's what I want you to imagine, okay? On both sides, the left side, you have commands in flight of 32. So some database application, lots of threads, okay? And on the right, it's maybe DD or something running, right? So imagine that you have a scheme that coalesces always two completions. The effective drop of commands in flight on the left would be down to 30, which is still pretty handsome. But on the right, it would be down to half. So that's our intuition, which is you can't just go and say, hey, I remove 2. You have to really think about what's actually happening, okay? And so with that, what we realized is something very interesting. So if you look at this plot, commands in flight on the x-axis and latency and throughput on the y-axis, as you all know, latency saturates, right? You can't, throughput saturates, latency doesn't. Latency always goes on it increases forever. Throughput, though, saturates. So now what that means is you can add more load but not get much improvement after a certain point in time, and probably a dip because of congestion. Okay, so what we noticed is that if your commands in flight is low, you're usually on the steep part of the throughput curve. Okay, but if your commands in flight is high, you're usually on the flat part of that throughput curve. So when you have lots of commands in flight, you can coalesce a lot. When you have less commands in flight, you can coalesce less. And if you do this, you can get huge improvements. Okay, so without going into kind of the details of that, here's the improvements that we saw. So remember how it would take me 6 months, maybe a year to get that 0.25% improvement in this benchmark called tpc-c? When we did this, we got 5%. Okay, so this has kind of been a lesson in my life, which is don't micro-optimize if you can avoid it. Try to actually deal with the hardcore problems, the structure of the algorithm, the structure of the system first, and that's where you're going to get the biggest bang for the buck. So there's a lot of details about what this plot means and so forth. Here's the key takeaways. That particular algorithm that I showed you is in production. Tens of millions of virtual machines have undergone that particular optimization over the last several years that system has been in production. And I think it's actually more than 50 million by now virtual machines. But I don't have a way to prove that. So my lessons coming out of this was, look, this is a really old problem, right? And even me working in that system for years, right? I didn't really attack that problem because like this is interrupts, right? It's been solved. It's a solved problem. Like why do I have to spend energy and effort there? But it turns out that even problems that are that old and even problems that Dijkstra solved, quote unquote, right? That there's still optimization opportunities. So that really is one of the times in my career where I really learned a lot, but also got a lot of courage. To go after hard problems and problems that otherwise look like somebody else has solved them, and we managed to squeeze a lot of performance out of it. But it is like standing on the shoulder of giants, and a little bit, yet a little bit of changes can improve a lot. So change the rules when they weigh you down, and hopefully this quick history and peeling back the history of the invention of the interrupts was interesting stories for you, starting from Dijkstra's hesitations all the way to how the evolution through hardware and then through virtual machines have improved our understanding of how these dynamic systems behave. So the question I want to think about and encourage you to think about is, how will we interrupt ourselves in 2056? Thank you.